Okay, so we are in the tunnel FET. I'm a little bit slow, but I give you. So let's start. What is the physics of tunnel FET? A tunnel FET, for example, this is a p-type tunnel FET. What is a p-type tunnel? If you remember, what is a p-type MOSFET? Can someone tell me how you bias the source drain? What do you do for a p-type MOSFET? What do you bias to? What do you put as source?
VDD.
VDD. What do you put at drain?
Ground.
Something lower than VDD. Okay, yes, you can say ground, right? How about gate?
VG, whatever the turn on voltage we require.
I mean, what is the range? How do you turn on the PMOS?
1.12 volts.
Huh?
Oh, P.
What voltage? For example, if VDD is 5, what voltage do you need to put to turn on the PMOS?
One threshold below VDD.
One threshold below VDD. For example, VDD minus
VT.
Yes. Okay. Right. But we can say the same thing. It doesn't matter. These are just the relative value, right? I can also say VDD equal to 0. I can transform to 0. Then this one I can transform to negative 3 volts, for example. This one I can transform to negative 1 volt. You see what I'm trying to say here, right? You can You can have say, okay, this was 5 volt, right? Let's say this is what was 4 volt, right? And this was how many? 2 volt, right? I can bias it 5, 2, 4 is the same as 0, negative 1, negative 3. Do you agree? It's just potential difference, right? Is that okay? Any questions?
No.
Great. So that's what I'm trying to say here. This is a tunnel FET. Look at this. Look at the difference. This is intrinsic. This is N. That's a regular MOSFET, right? On the right. This is P plus. This is P plus. Okay, good. At least we have one that is the same. P plus, P plus. Okay. And this is N plus. This is P plus. So for a p-type transistor, it's actually just NIP. And what do? We apply negative voltage to here. This is the drain. This is the source. This is the gate. Okay.
Professor, did you draw it for NMOS?
Can you say again?
Like this is a transistor, right? Drain and source should be of the same concentration. Like even drain should be N plus, right?
But I'm talking about TFET, tunnel FET, a new type of device, not this one, right? This is regular PMOS. This is P-type tunnel FET. This is a new type of device. Do I answer your question?
Yeah, so basically it has a drain as P-type and source as N-type. That's what it is?
Yes.
Okay.
So this is a new type of device. You don't know how it operates yet, right? You feel very confused because you think that it's not going to work. We should use this one, PPN, right? But this is a regular one. Right? Now I try to show you what is the difference between a regular transistor and a tunnel FET. So what happened? Draw the Venn diagram. This is at 0 volt. And this is, let's say, at negative 3 volt. Do you see that? This is the valence band. This is the conduction band. As we have learned before, when you put this as 0, this is -3, you're going to push up the band, correct? That's why this one go up. At the same time, you have this intrinsic region. Anyone tell me what is intrinsic region? What's the meaning of intrinsic?
No doping.
Right, undoped. So it means the Fermi level is at the middle, right? Here we don't care that much. When this one is at 0 bias, this one, blue, Vg equal to 0. You get this band diagram. Is that okay? For the blue one, that's how you draw the band diagram. What happens if Vg becomes negative how much? 1 volt. Just based on what we learned before, you push up the band diagram, right? Then you have the red one. Is this okay? Now, how about let's look at the blue. Can you tell me, is there any current if I'm in the blue situation with Vg equal to 0? Is there any current? Just use all the knowledge you have learned in device physics. Is there any current?
Just the leakage current?
Just the leakage current. Very good. I have -3 here. I try to push the electron to here. Well, actually, you will conduct well. But the problem is this is p-type. PN junction is reverse bias. I don't have much electron. So this is the leakage current. I have negative here, which is positive related to this one. I can push the hole to this side easily. But this is N-type. I don't have much electron. So at the blue, I only have the leakage current. The leakage current of PN junction. I call it PIN diode, right? It is just a PIN diode. We call it PIN. P intrinsic and N region. Very small. How about when I increase the gate voltage to -1? Do I have current?
Not until that's equal to VT minus VTH.
VTH is something for the circuit designer. We are device designer now, right? We don't care about VTH. We look at the physics. So you cannot just tell me that not after VTH. Look at the current diagram. Do we have current?
Current starts growing slowly.
Say again?
The current will start increasing slowly.
But you need to explain to me why it will increase slowly.
It will insert the electrons.
Impact ionization.
Okay, good. Someone say impact ionization. So first of all, you will say maybe there is more current, but
Or just tunneling.
Okay, yeah. I'm going step by step. You guys all get it, okay? So now, the current here, you're just increasing this. I still try to push electron from here. Still, I don't have much electron, correct? Same for hole. Still, I don't have much hole. So no matter how you put this one up and down, my current is very similar because the drain and source voltage is the same. Do you agree? Everyone agree what I say now? It's just a diode, correct?
Yes, Professor.
Thank you. Now, then you say, someone say impact ionization. Very good. Now, can you tell me why there's impact ionization?
At the beginning and the end?
Where, what beginning? Can you be more specific?
Far left and far right.
You mean here?
No, at the interface.
Here?
Yeah.
Okay. Can you say why here I have impact ionization?
It's a steep band gap.
Very good. It's very steep slope, which means you have very high electric field, right? How about here?
Not so much, but
Good. Not so much. Actually, it get less. The electric field is smaller. Okay. So what you're saying is very good, right? So this can be an issue, but for this particular device, this one happened later, right? So you are perfectly correct. The only thing is we need to really do the calculation to see how large the impact ionization is. Okay, so yes, there can be impact ionization. Okay, very good. And then, but this is not the answer. Not the answer, not because you're wrong, you're right. But in this particular device, something take off first. Okay, that is the last thing you say. Someone say tunneling. Can you explain what you mean by tunneling?
well, there would have to be traps all along.
Do you need traps?
Yeah, right. I mean,
From where to where tunneling? From where to where?
perhaps on the interface.
You mean here?
No, the oxide interface or the insulator interface.
Okay, but what we are talking about is across this cross section, right? Let's say we have a perfect interface. Okay, no traps.
Is there traps in the body, in the bulk?
No traps. Perfect. Everything is perfect. And in this device, tunnel FET, we don't want to have traps. If you have traps, you reduce the subthreshold slope. Okay. But tunneling is still playing a very important role. Can someone tell me what tunneling is going on? And that is the physics of tunnel FET. Remember, this is called tunnel FET. It is the tunneling that is giving the physics. Anyone?
From the Fermi level on the left side at the source to the Fermi level to the valence level.
Yes.
Yeah.
What do you call this type of? So to be more specific, right? Not Fermi level, but from the conduction band of the source to the valence band of the channel.
Right.
What do you call this type of tunneling?
Band-to-band tunneling.
Thank you very much. This is the band-to-band tunneling of hole. But in the blue, isn't that we also can, why we don't have, why I say that there's only leakage of PN diode for the blue, that is where VG equal to 0. Right, it's a little bit messy here, but the blue is this one. This is the valence band. This is the conduction band. Do we have band-to-band tunneling in this case? We have the same drain voltage and same gate voltage here. Do we have band-to-band tunneling in this case when VG equal to 0?
Well, there's an electric field.
Yes, electric field, exactly. Let's assume the electric field is also very high. Do you have band-to-band tunneling in this case?
I believe so.
You believe so. But band-to-band tunnel is from where to where? Can you repeat? From which band to which band?
From valence to conduction.
Yeah, or in this case, from conduction to valence band, right? Can this one tunnel to valence band when it is VG, when VG equal to 0?
Probably not.
Yeah, because they are not aligned. I'm at this level. I can only tunnel to the same energy. But this one has lower energy than me. This is just quantum mechanics. I cannot lose the energy when it is blue. So as a result, before the valence band touch the conduction band level, I don't have any band-to-band tunneling current. So my current is very low, just leakage. Once the valence band of the channel is at the same position as the conduction band or Fermi level of the source, that is this level, then I can start having band-to-band tunneling. And the whole tunnel to here, then they will just drift to here. Remember I said that we want the hole to come here. It is easy, but we don't have hole from the source because this is N-type. But now I tunnel the hole into the valence band, then they can move to here. That's why the current will go up. And now answer the question. Just now you talk about threshold voltage. The threshold voltage of tunnel FET is at which your valence band at the channel align with the conduction band of the source. Is this okay? I know I am talking, right? But it's easier to talk. I mean, I will give another example later. But this is a very nice diagram. That's why I want to stick with it.
Why does it have to be intrinsic?
Why it has? You mean the doping?
Yeah.
I mean, just think about it can be others, right? But if you make it exactly N and let's say this is N plus, then you are going to need to apply very high gate voltage to turn it on. And then you also have a very steep gradient between N and P. So just now you also say that this, then you will have a very steep gradient here. You might have band-to-band tunneling or impact ionization in this region.
I see.
Yeah, let me draw it, but I will erase in case. If you actually have a N plus region, then this one will go up together with this one, right? When there's when it is at low bias, right? Then you have I should not draw this way. You might have something like this, right? Then you have a very narrow region. Then you may have band-to-band tunneling. So there are many considerations. I might not answer it well, but this is one reason that you want to be intrinsic. Any other questions?
Professor, I had one question.
Yeah.
So here we're trying to see that when we apply gate voltage, there's a band-to-band tunneling, as we can see on the left side of the graph, from the conduction band to valence band, and that is how the conduction takes place.
Yes.
Okay, and what does the P part of the diagram explains?
What is what? Say again.
The band diagram for P type on the right hand side, the drain.
The band diagram. What is the role of this part?
Yeah, I exactly don't understand. Is it just simple that the valence band is above the?
Yeah, this is because the drain is biased at -3 volts, so it goes up.
And the Fermi level is below the valence band, so doesn't it mean that it has a lot of holes?
Because it's P-type, so it has a lot of hole. Yes. This is N-type, so it has a lot of electron. That makes sense?
Yes, Professor.
Okay. Right, so if this is band-to-band tunneling, then why it has steeper slope? Just because of the physics of band-to-band tunneling, right? Instead of fermionic emission. Okay, it's using a different physics, so it has a steeper slope. And also it has something filtering effect. You see, only this green portion can tunnel. Those with higher energy, lower energy, it should be lower for hole, cannot tunnel because here is the gap. Those with lower energy also cannot tunnel because you don't have those with lower energy, right? So it has an energy filter effect. That's okay. I just I just want you to know this. I don't care if you really really understand, but the point is, you see, the whole thing is cut off. Only this region can tunnel. So you can see that definitely band-to-band tunneling depends on this lambda, the thickness, and it also depends on how much overlap your valence band in the channel and the conduction band in the source, right? When I increase VG, what happened? Lambda gets smaller. I mean, make it more negative. Lambdas get smaller. At the same time, delta phi get more. So here you see that the tunneling probability depends on lambda and delta phi. They all change at the same time. This is larger, this is smaller. That's why you get super exponential. And this one gives you less than KT over Q. KT over Q is also, fermionic emission is also exponential. But this one is super exponential. It goes faster. So that's why theoretically, this one has a steeper subthreshold slope. Is that okay? Any questions? And on the right here shows the VG, right? When the VG increased, and then what happened to the current? First leakage, and then here you have band-to-band tunneling. Now, the best is that let's do a exercise together, right? And I actually changed the slides this year because I thought that it's easier to understand. So forget about this 9. Okay, we did the p-type already. So what is n-type? All right, I can tell you, this is the n-type. It's still PIN, okay? But then P on the source and N on the drain. I apply a positive voltage, for example, 3 volts, and then this one maybe apply 1 volt, and here is 0 volt. Okay, let's say at the beginning, right? Let's do this carefully. It is 3 volt. First of all, I know that on the left, what do I have? I have P. On the right, I have N. Right, maybe heavily doped. Let me just put it really next to each other. Right, this is 3 volts. And then the curve is going to go down like this. Right, you just join them. It's intrinsic in the middle, right? So then you have something like this. And let's say the gate equal to 0 volt. This is the case. So in this case, do I have current? Again, I don't have current because, well, electron like to go here, but very few. This is p-type. Hole like to go here, but again, this is n-type. So this is what? Just a leakage, right? And actually, shamelessly, actually, I obviously did not draw it well, right? You see the Fermi level, they are almost the same from the left and right. I probably need to move this one maybe lower, a little bit lower. I just reduce the band gap maybe. Right? Maybe make the band gap smaller. The drawing smaller. Then this may make more sense, right? So that you have a lower band, because so that this is 3 volts. Is that clear for you at this stage? Any questions? Now, what happens if I apply a high gate bias? What happened to the middle parts if I apply a high gate bias? Can someone tell me? What will I change to the channel?
Valence and conduction band overlap.
Wait, okay. Okay, but before that, just tell me what happened to the channel conduction band and valence band. How would they move?
Down.
Both down, very good, right? So then this one will move down. Okay. Right, this is VG equal to, let's say, 2 volt. Right, let me use 2 volt. Then what happened when you move down? Do I have current?
Yes.
Why?
Well, the slope has decreased. It's become.
The slope,
Electron tunneling.
right. The slope has decreased, has increased. Yes, that's true. But still, I only have that few electron in P plus at that few hole in N plus, right? Yes, I can get the electron here, but still I don't have enough source. The current is still very small. But just now you also say that I can have band-to-band tunneling of electron. Okay, then it is different. I don't have a lot of electron here, but now after tunneling, I have plenty of electron. They just go to the string, right? Electron go to the high potential. Then the current shoot up. Right? So in summary, it is this. At the conduction band, intrinsic conduction at off states, right? Which is the, let me still change the color. This is off states. Conduction band of the intrinsic region is above the valence band of the P plus region. So no band-to-band tunneling. So very small current, right? And then what happened? When we go to on state with high VD, high VG, conduction band of the intrinsic region or the channel is what of the valence band of the P plus region? Anyone? I should not say off, right? Off is really wrong grammar, right? So at the on states, right? When I have large VG, the conduction band, this one of the channel or the I region is where of the valence band of the P region?
Lower.
Below, yeah.
Yeah.
Right? So do we have current? Yes. A lot of B10, two band-to-band tunneling. Okay, so now go back to your original question, right? Just now at the beginning, someone say, this is not a transistor. How come P and N? You have a PN diode, right? This is N type, PIN. This is P type, NIP. Okay, just remember they're just PIN, NIP. For PMOS, drain is at P. For NMOS, drain is at N. And they don't work usually, but because we try to use the band-to-band tunneling effect, what we did is use the gate voltage to modify the band so that we have a very narrow tunneling region. Suddenly, a lot of current go through because tunneling band-to-band is turned on. And due to this super exponential, remember WKB approximation, you don't need to derive it. But now you should know that WKB approximation tells that the tunneling is more if you have thinner barrier, and then if you have a smaller bank, smaller gap. When this is higher, then the barrier is less, right? The height is less. And that's all. This is about the theory of the tunnel effect. Any questions? If no, right? Let's move forward. Tunnel effect has its own problem. You see that I thought that one of you was trying to ask just now. Now you see that if I put a let's say, can you tell me what type of device this is? N type or P type, by the way? See if you remember what I say. It's a PIN, right? And the N is at the drain. So this is P type or N type?
N type.
N type.
N type.
N type. Yeah, thank you. Remember, look at the drain, then you know. Okay, this is N type. So if N type means a positive voltage, positive VG, I'm going to get a lot of current. Of course, it does. This is 9 plus 1 volt gate. A lot of band-to-band tunneling, right? Well, but the problem is, what if I bias this to negative 1 volt? What happened? Then you go up. Hey, I also can have band-to-band tunneling. I still have current. And that is what you see here. When you go to high VGS, you have the regular curve like what we have, right? So in a regular transistor, this is regular. And if we don't consider Gitto, right? If no Gitto, I talked about Gitto before, but not going to spend time here. I guess you might also forget, but Gitto means that you are going to get up again. This is VG. This is ID. Well, I don't expect it to turn on, right? It's just like a water, like the water tap. You turn it, what, clockwise or counterclockwise. You turn on the water, then you turn clockwise. You turn off the water. What if I turn more? You expect that you keep turning. You should keep reducing the current, right? But just like water tap, if you keep turning, you dare to turn more, you're going to break it, and then you're going to have a lot of water again. This is not breaking. This is just the physics. You push this down, give a thin barrier. I got band-to-band tunneling. You pull this up by negative bias. I also get this part thin. I still get band-to-band tunneling. So both of these contribute the current, which is not good. We don't like that. Because in a CMOS, your N-type is going to experience negative gate bias to the source in some instance. If that is the case, then it is not off. You are going to have leakage. So what can we do? Then you can think, can I do something so that when it becomes negative, the bending is not so much? And that's what they do by having an overlap between the gates. With an overlap between the gates, right? So when we have a high bias, yeah, we have very thin barrier. So I have band-to-band tunneling. I have a lot of current. But if I have very negative bias because of this overlap and because of electrostatics, I have very thick barrier for BT-BT just because of the electrostatics. Then in that case, you see that if I can increase the overlap region, then I have a very large region that doesn't have leakage, right? And if my device is operate between negative 0.5 and 0.5, then I'm okay. This behavior is called bipolar. You conduct in both directions of the VGS. Right? We always say transistor only conduct when it's larger than VTH. But this transistor, if you don't do it well, it conduct when it's very negative, right? That is the point. Any questions? If no, let me move forward, right? So how can we improve the tunnel FET performance? We want to have a high ion, right? Small subthreshold slope, and then high ion-I-off ratio, right? So we can make the band gap smaller, reduce the effective mass and the lambda. This is the lambda, the tunneling width, okay? How can we reduce it? It really depends on the geometry, right? Just look at this. Because I have this overlap, the effective lambda is larger. That's why I can suppress the bipolar behavior. So the design of the whole transistor is very important to determine how steep it is. Okay, and we make it as one-dimensional as possible because we want the tunneling all go laterally. We don't have a do not want to have a two-dimensional one. Okay, we make the junction as abrupt as possible. Okay, and then this is a like counter to what I just say at 1 PIN, right? But basically what you try to say is you overall you want to this one this is not very clear. When we say abrupt, we are talking about the gradient. So not really if I want to be more specific, I should say the P and I junction or I and P junction, I or N junction, right? You want to add very abrupt. It means that you want to have doping profile like this. For example, this 10 to the power 20, and suddenly you go to 10 to the power 10. This is the I region. And then in the other side, you go to negative 10 to the 20 because it's N type, right? Very abrupt instead of something like this. We don't want this because this is going to determine how good your lambda and also how fast it turns on. An interesting thing is up to now, we never talk about LG. It's all about this band-to-band tunneling. So actually, the good thing about, or maybe bad thing, depends on how you see, about tunnel FET is it doesn't depend on LG. So you can scale it. It doesn't increase the current much. However, it reduces the capacitance, right? So that is the point, right? Any questions? So after all, for tunnel FET, what I want you to know is the mechanism. You understand that you apply a high bias, suddenly you turn on the band-to-band tunneling by playing with this, by applying a gate bias, making very narrow. And it has a bipolar behavior. And whatever can change the band-to-band tunneling can be used to optimize the tunnel FET. That's the focus. So how can we further improve it? One possibility is to use different material, right? For example, here, instead of using silicon everywhere, we use germanium in source only. Why this is good? Because it has a smaller band gap. So it have more tunneling. When it has more tunneling, then I have a higher current. For the rest, I still use silicon. This is still silicon. Can you tell me why I don't use germanium there? Why it is good to use silicon? I use germanium on the left is to have more band-to-band tunneling. Do I want to have a lot of band-to-band tunneling at the right? In all our discussion, did we try to have band-to-band tunneling between the drain and the channel?
No.
No, right? Because to avoid band-to-band tunneling. We don't want to, because if it has, then we run into this problem and bipolar behavior. You might actually have more current in the negative bias in that case. Okay. And for P-type, right, we need actually use indium arsenide just because of the band alignment, right? So here we are tunneling from this here to here. This is tunneling the hole to here, right? So we want it have an alignment like this. Here we're tunneling electron to here. Germanium has a better band alignment. So that's why we choose germanium. Okay, so you can improve the performance by using hetero material. And here shows some of the results. First of all, if I use indium arsenide, you see the lambda is much smaller. So I have a lot of tunneling. Germanium is this, silicon is this. So if I use all silicon tunnel FET, it has low current. But once I use germanium, you see the current increase a lot. Slope is also better. So on-off ratio is better. And here you also can see that their slope is kind of better than the MOSFET, but not a lot actually. It's not easy to have a very good slope. Okay, any question about the tunnel FET?
Yeah. So do we use this currently?
I don't know if they're in the production. Maybe, I don't know. Yeah, maybe needed to Google. STT-RAM, what we are going to discuss. They are in the production in real application already. But tunnel FET,
Is it relatively new?
it's not really that new, but you need to find a niche market. You see, everything has to be changed, including the fabrication process, and it's the best when you are using nanowire or now the best performance one. So that's why I think it's not in the market yet. The best performance is nanowire, but in order to make nanowire, even now the technology, we start having nano chip, but nanowire is still not that mature. Tunnel FET has a problem. Just now you talk about trap. If you have a trap assisted tunneling, if you have a lot of trap here, you actually can get a lot of leakage. Then you don't have that high subthreshold slope, right? Before your channel valence band align with the source conduction band, there's no tunneling. But if you have a trap, then you have trap assisted tunneling or phonon assisted tunneling. Then they can tunnel into your valence band. Even they can have the same energy. Here we're talking elastic tunneling, so you have the same energy. So in that case, then you have a worse performance. So there's still a lot of things to solve in the tunnel FET. But I don't know if they're in production. I mean, of course, definitely they have a lot of experiment going on in the foundry. Yeah. Okay. Any other questions?
Yeah. So is there any I guess the question is, can we leverage traps, right? Is there anyone that uses or a design that leverages traps as part of the physics?
But as just said, trap is worse. How do you want to leverage it? Right? You can leverage, but what is your purpose? How do you want to? Which physics make you think that you can make it have a steeper subthreshold slope?
Yeah, I mean, I guess it's just, I mean, what I was thinking is if you're going smaller, right, you have to work with the physical problems that you're presented, which is tunneling and traps. So I guess I thought that the tunnel FET would be the solution to smaller sizes, right, below 7 nanometer, for example.
Yeah,
but this is like 100 nanometer, right?
Yeah, you can make it smaller, but why do you think the trap is going to help?
Well, just because it's not avoidable. So
yeah, so yeah, it's unavoidable is one thing, right? That's good. You say because it's unavoidable, let me use the trap. But however,
right.
So far, in terms of the physics of tunnel FET, we don't see how trap can help. But
I see.
You may, if you can find out, probably you came up with a new device. So now all the tunnel FET, you can see all the paper, they actually try to say that I am able to remove the trap. And they also try what? They try to do cryogenic cryogenic experiment. In cryogenic, like 77 Kelvin, the trap has less effect. And then they will get better result.
I see.
Yeah. So this is a very good question, right? So the point, good that you say that something unavoidable, try to use it.
Mm-hmm.
Yeah. Try to see if you can come up with some good idea, right? And if you can prove in TCAD or some calculation, you can even file a patent.
Mm.
Yeah.
I see.
Yeah. Any other questions or comments?
I do have a small question, just totally outside of the field of what we're talking about right now.
Mm-hmm.
But so there's the new atomic the surface scanning microscope, right? They were showing how they were able to recently. There was a paper showing how they were able to pretty much scan the size of one atom by tunneling, by switching, by using radio waves to switch the spin of the protons in an atom, and then measure the change in the I believe the electron field around the atom, right? So I guess I was wondering if there's any physics devices, right, that leverage gaps between one side and another to then use tunneling, where it's going through a gap rather than going through a medium.
Exactly. Good question. This is something people also look at. It is called vacuum FET, right? But it's not in the mainstream.
Mm.
It actually heavily studied by a guy in NASA, and I know him. We are also collaborating, but he did not do this much now. Vacuum FET. Why we need to do that? If I can emit electron to the vacuum, there's no scattering, right? It doesn't have to be vacuum, actually. Even air is okay because it's so small. Within 10 nanometer, you might not even able to find an air molecule. So basically, they are traveling ballistically. And this goes back to the vacuum tube. It's exactly the same physics. The difference is just that in the past, it is a very large, bulky, also unreliable vacuum tube we need to heat out. But now we want solid state. It is on the wafer, mass production. But why it was so unreliable at that time? Because to heat up, to emit the electron to vacuum, you need to heat up the filament, just like the old time, the filament, the bulb, right? The light bulb, okay?
Right.
And that's why you keep heating up, then you are going to die because the constantly evaporating, the atom is going to evaporate. Here, what we do is just use a very high electric field because of the, make a very sharp tip. You have very high electric field. The electron will just emit easily through tunneling. This is also a type of tunneling.
Right.
This is your conduction band, and this is the vacuum level, right? If you high electric field, basically make the vacuum level like this. Then electron can tunnel through. Then they go to the vacuum. Okay, so this is the called vacuum FET. So good, right? Good idea, right? So this is something you can think about, but there are many more ideas, but always there will be limitation. For example, here is how can you emit electron efficiently? Although you rely on high electric field, it's not that good in terms of the on current still. And then another problem is, how about the gate, right? I also did some simulation for this device. The electron can go to the gate easily. You don't have an insulator because now you are at vacuum. You are vacuum, you can go to any material. Think about that, right? Just you have a molecule in the air. You can stick to anything on the or in your room. So there's no insulator. I get a lot of gate leakage in my simulation.
Is this TCAD? Did you use TCAD for this?
I try to use TCAD, but TCAD is not that suitable. Because TCAD assumes that you have an effective mobility, you cannot do ballistic transport, but still you can do some electrostatic study. Yeah. Okay. Yeah. Okay, so sorry, time's up. So I need to
Okay.
stop here. Yeah.
Thank
Any
you.
other questions?